the story of a star's final breath. Every star has a story. It begins in darkness, in clouds of gas and dust that collapse under their own weight, igniting fusion in their cores. For millions or billions of years, stars burn steadily, balancing gravity's inward pull with the outward pressure of nuclear fire. But nothing lasts forever. When a massive star exhausts its fuel, when there's nothing left to burn, gravity wins. The core collapses in less than a second. The outer layers rebound in a catastrophic explosion. This is a supernova, a star's final breath, its last grand gesture before fading into something else entirely. Some stars go quietly, shedding their outer layers and leaving behind a cooling ember. But massive stars, those born with 8 times the sun's mass or more, die spectacularly. They explode with such force that for a brief moment, they become the brightest objects in the universe. The story of a star's final breath is written in light across the cosmos. The end of stellar life. Stars are not eternal. The end of stellar life comes when the delicate balance between gravity and pressure collapses. For most of a star's existence, fusion in its core generates enough outward pressure to counteract gravity's crushing force. But fusion requires fuel, and fuel is finite. Small stars like our Sun will burn for trillions of years, slowly exhausting their hydrogen, eventually cooling into white dwarfs. But massive stars live fast and die young. They burn through their fuel in mere millions of years, fusing heavier and heavier elements in their cores. Hydrogen to helium, helium to carbon, carbon to oxygen, all the way to iron. Iron is the end of the line. Fusing iron doesn't release energy, it consumes it. When the core turns to iron, fusion stops. Without the outward pressure from fusion, gravity takes over. The end of stellar life is swift and violent. The core collapses, and the star's outer layers explode outward. What remains is a remnant, a neutron star, or black hole, and a cloud of glowing gas expanding into space. Earth, but with more mass than the Sun, suddenly loses its support. The moment of collapse is almost instantaneous. In less than a second, the core shrinks from thousands of kilometers across to just 20 or 30. Gravity compresses matter to unimaginable densities. Electrons are crushed into protons, forming neutrons. The core becomes a neutron star, so dense that a teaspoon of its material would weigh billions of tons on Earth. The collapse releases an enormous amount of gravitational energy. Most of it escapes as neutrinos, ghostly particles that barely interact with matter. But some of that energy drives a shockwave outward through the star's outer layers. The moment of collapse is the trigger, the point of no return. Everything that happens next, the explosion, the light, the creation of elements, flows from the single, catastrophic instant when a star's core can no longer hold itself up. The explosion that shakes the cosmos, the shock wave from the collapsing core, tears through the star's outer layers at thousands of kilometers per second. The explosion that shakes the cosmos is almost beyond comprehension. In a matter of hours, the star's outer envelope is blown into space, carrying with it the elements forged in the star's lifetime. The explosion releases as much energy as the Sun will produce in its entire 10 billion year life, all in a few seconds. This energy heats the ejected material to billions of degrees, causing it to glow brilliantly across the electromagnetic spectrum. The explosion doesn't just destroy the star, it transforms it. The intense heat and pressure create elements that couldn't form in the star's core: gold, platinum, uranium. These heavy elements are forged in the chaos of the explosion. The explosion that shakes the cosmos sends these elements flying into space, enriching the interstellar medium, seeding future generations of stars and planets. Without supernovae, the universe would be a simpler, less interesting place. No rocky planets, no complex chemistry, no life. The brightest light in the sky. For a few weeks, a supernova can outshine everything. The brightest light in the sky isn't the sun or the moon, but a dying star billions of light years away, visible even in daylight if it's close enough. Ancient astronomers called them guest stars or new stars, not understanding what they were witnessing. The brightest light in the sky comes from the explosion's energy heating the ejected material. As the shock wave plows through the star's outer layers, it compresses and heats them, causing them to radiate intensely. The light peaks within days or weeks, then gradually fades over months or years as the expanding debris cools. At its brightest, a supernova can reach absolute magnitudes of -19 or more, meaning it's billions of times more luminous than the sun. If a supernova occurred just 10 light years from Earth, it would appear brighter than the sun in our sky. Fortunately, no stars that close are candidates for going supernova anytime soon. The brightest light in the sky is both beautiful and terrifying, a reminder of the violent processes that shape the cosmos. The death that creates new worlds. Death and creation are intertwined in the cosmos. The death that creates new worlds is how supernovae enrich the universe. When a star explodes, it scatters heavy elements into space: carbon, oxygen, silicon, iron, and all the elements heavier than iron, forged in the explosion itself. These elements mix with the interstellar medium, the gas and dust between stars. Over time, this enriched material collapses to form new stars, and around those stars, planets. The death that creates new worlds means that every atom in your body heavier than hydrogen was created in a star or supernova. The carbon in your cells, the oxygen you breathe, the iron in your blood, all forged in stellar furnaces and scattered by explosions. The death that creates new worlds is the ultimate recycling program, the universe's way of ensuring that matter doesn't stagnate. Stars live, die, and in dying, provide the raw materials for the next generation. This cycle has been repeating for billions of years, gradually enriching the universe, making complex chemistry and life possible. The birth of a supernova. A supernova isn't born, it's made. The birth of a supernova is the culmination of a star's entire life. For a massive star, that life is a race against time. The star burns hydrogen, then helium, then heavier elements, each stage shorter and more intense than the last. Hydrogen fusion lasts millions of years. Helium fusion lasts hundreds of thousands. Carbon fusion lasts centuries. Silicon fusion lasts days. Finally, the star fuses silicon into iron, and within hours the core is full of iron. The birth of a supernova is this moment when the iron core reaches critical mass, when gravity, finally, overwhelms the forces holding the core up. The core collapses, and the supernova is born. It's not a gradual process. It's sudden, catastrophic, inevitable. The birth of a supernova is the death of a star, but it's also the beginning of something new. The explosion creates elements, triggers star formation, shapes galaxies. In death, the star gives birth to countless futures. The core that can't hold on. At the heart of every massive star nearing its end is a core under tremendous pressure. The core that can't hold on is fighting a losing battle against gravity. For most of the star's life, nuclear fusion produces enough outward pressure to balance gravity's inward pull. But as heavier elements accumulate in the core, fusion becomes less efficient. Iron doesn't release energy when it fuses. It absorbs it. When the core turns to iron, fusion can't help anymore. The core that can't hold on is now supported only by electron degeneracy pressure, a quantum mechanical effect where electrons resist being squeezed into the same space. But even this has limits. If the core's mass exceeds about 1.4 solar masses, the Chandrasekhar limit, electron degeneracy pressure can't support it. The core collapses. The core that can't hold on finally gives way, and in less than a second, it shrinks from thousands of kilometers to just tens. The collapse is so rapid, so complete, that it's almost incomprehensible. The core that can't hold on becomes a neutron star, or if massive enough, a black hole. The pressure that finally breaks. Inside a dying star, pressure is everything. The pressure that finally breaks is the moment when the core's internal forces can no longer resist gravity. Throughout the star's life, pressure from nuclear fusion, from the motion of particles, from quantum effects, has held the core up. But as the core grows denser and heavier, gravity's pull intensifies. The pressure that finally breaks comes when the iron core reaches critical mass. There's no more fuel to burn, no more energy to generate outward pressure. Gravity wins. The core collapses, and the pressure that finally breaks is released in the form of a shock wave that tears the star apart. This isn't a gentle transition. It's a catastrophic failure, a sudden and complete loss of equilibrium. The pressure that finally breaks has been building for the star's entire life, held in check by fusion. When fusion stops, the pressure has nowhere to go but outward. In an explosion so powerful, it can briefly outshine an entire galaxy. The gravity strong enough to end a sun. Gravity is the weakest of the fundamental forces, yet on cosmic scales, it dominates. The gravity strong enough to end a sun is what ultimately causes supernovae. For most of a star's life, gravity is balanced by other forces. Pressure from fusion, from heat, from quantum effects. But gravity is patient. It's always pulling, always waiting. The gravity strong enough to end a sun finally wins when the core runs out of fuel. Without fusion to counteract it, gravity compresses the core to extreme densities. Atoms are crushed. Electrons merge with protons. Matter is compressed to the point where quantum mechanics struggles to describe it. The gravity strong enough to end a sun is what creates neutron stars. Objects so dense that a sugar cube-sized piece would weigh as much as all of humanity. It's what creates black holes, regions where gravity is so strong that not even light can escape. The gravity strong enough to end a sun is a reminder that gravity, though weak, is inexorable. Given enough mass and time, nothing can resist it. The chain reaction. Inside a dying star, a massive star's death is a cascade. The chain reaction inside a dying star begins when silicon fusion produces iron in the core. Iron accumulates, and as it does, the core grows heavier and denser. Gravity intensifies. The core compresses. Temperature and pressure rise, but iron won't fuse. It only absorbs energy. The chain reaction inside a dying star accelerates. As the core grows heavier, it reaches the Chandrasekhar limit. Electron degeneracy pressure fails. The core collapses. The collapse releases gravitational energy. Neutrinos flood out. A shock wave forms. The shock wave plows through the star's outer layers. Those layers heat up, ignite, explode. The explosion scatters material into space. The chain reaction inside a dying star is irreversible. Once it begins, nothing can stop it. The star's fate is sealed. Within hours, a star that has burned for millions of years is torn apart. The chain reaction inside a dying star is nature's domino effect, each event triggering the next, culminating in an explosion that releases more energy than most stars produce in their entire lifetimes. The fusion that burns to its limit. Nuclear fusion is what makes stars shine. The fusion that burns to its limit is the star's life story. It begins with hydrogen fusing into helium in the core. This process releases energy, which creates the outward pressure that balances gravity. As hydrogen depletes, the core contracts and heats up, eventually reaching temperatures where helium can fuse into carbon and oxygen. The star continues this pattern, fusing heavier and heavier elements. Carbon fuses into neon and magnesium. Neon fuses into oxygen and magnesium. Oxygen fuses into silicon and sulfur. Silicon fuses into iron. The fusion that burns to its limit stops at iron. Iron is the most stable nucleus. Fusing it doesn't release energy, it consumes it. When the core turns to iron, fusion can't continue. The fusion that burns to its limit has reached its end. The star has exhausted its nuclear options. Without fusion to generate pressure, the core collapses. The fusion that burns to its limit is a one-way journey up the periodic table, each step shorter and more desperate than the last. The iron core that seals its fate. Iron is stable, too stable. The iron core that seals its fate is the endpoint of stellar fusion. Unlike lighter elements, iron can't release energy through fusion. Fusing iron into heavier elements requires energy rather than releasing it. So when a massive star's core turns to iron, it's a death sentence. The iron core that seals its fate grows as silicon fusion continues in a shell around it. As the core accumulates iron, it becomes heavier and denser. Gravity intensifies. The core compresses. Eventually, it reaches the Chandrasekhar limit, about 1.4 solar masses. At this point, electron degeneracy pressure, the quantum force supporting the core, can't hold anymore. The core collapses. The iron core that seals its fate is like a ticking time bomb. As soon as silicon fusion begins, the clock starts. Days, maybe hours, and the core will collapse. The iron core that seals its fate is the star's final chapter, the element that marks the end of fusion, the beginning of collapse, and the inevitable supernova to follow, the energy released in seconds. When a supernova explodes, it releases an almost incomprehensible amount of energy. The energy released in seconds is equivalent to the total energy output of the sun over its entire 10 billion year lifetime. In just a few seconds, the collapsing core releases about 10 circumflex 53 ergs of energy, a number so large it's difficult to conceptualize. Most of this energy escapes as neutrinos, which barely interact with matter and stream out of the star at nearly the speed of light. About 1% of the energy goes into the explosion itself, heating and accelerating the star's outer layers. The energy released in seconds is what tears the star apart, what creates the light we see, what forges heavy elements. It's a sudden, violent release of gravitational energy. The core's mass collapsing creates a gravitational potential well, and falling into that well releases energy. The energy released in seconds is nature's most powerful explosion, rivaled only by gamma-ray bursts and the Big Bang itself. It's a reminder of the tremendous forces at play in the universe. The power of a billion suns. At its peak, a supernova shines with the luminosity of billions of suns. The power of a billion suns is concentrated in a single point, a dying star briefly becoming the brightest object in its galaxy. This isn't a sustained output. The supernova brightens over days, peaks, then fades over weeks or months. But at maximum, it's brilliant beyond imagination. The power of a billion suns comes from the explosion heating the ejected material. As the shock wave tears through the star's outer layers, it compresses and heats them to billions of degrees. The hot, expanding gas radiates across the spectrum: visible light, ultraviolet, X-rays. The power of a billion suns is visible across vast distances. A supernova in a nearby galaxy can be seen without a telescope. A supernova within our own galaxy would be visible in daylight. The power of a billion suns is both a beacon and a warning. Beauty and violence intertwined, creation and destruction happening simultaneously. A reminder of the energies that shape the cosmos. The shock wave that tears through space. The explosion creates a shock wave that propagates through the star's outer layers and into space. The shock wave that tears through space travels at thousands of kilometers per second, carrying energy, momentum, and heavy elements. As it plows through the star's envelope, it heats the gas to extreme temperatures, causing it to glow. When the shock wave reaches the star's surface, it breaks free, expanding into space. The shock wave that tears through space doesn't stop when the star is destroyed. It continues outward, plowing through the surrounding interstellar medium. Gas and dust are swept up, compressed, heated. The shock wave creates a bubble of hot, glowing gas, a supernova remnant. Over thousands of years, the shock wave slows as it sweeps up more material, eventually dissipating. The shock wave that tears through space shapes its environment, compresses gas clouds, triggers star formation. It's a wave of destruction that also seeds creation, a force that reshapes the galaxy on scales of light years. The shock wave is the supernova's legacy, its impact felt long after the light fades, the light that outshines a galaxy. For a brief time, a single dying star can outshine an entire galaxy. The light that outshines a galaxy is one of astronomy's most spectacular sights. A galaxy contains hundreds of billions of stars, yet a single supernova can briefly be more luminous than all of them combined. The light that outshines a galaxy comes from the energy of the explosion heating the ejected material. As the shock wave plows through the star's outer layers, it deposits energy, heating the gas to billions of degrees. The hot gas radiates intensely, glowing across the spectrum. The light peaks within days or weeks, then gradually fades as the expanding gas cools. The light that outshines a galaxy is why supernovae can be seen from Earth, even when they occur in distant galaxies, billions of light years away. Ancient astronomers saw them as new stars appearing where none existed before. The light that outshines a galaxy is a testament to the energies involved, to the violence of stellar death, and to the universe's capacity for spectacular displays. The moment the star becomes dust, after the explosion, the star is no more. The moment the star becomes dust is when its outer layers, blown into space, fragment and disperse. What was once a coherent object, a star with structure, layers, a core, is now a cloud of gas and dust, expanding into the void. The moment the star becomes dust is gradual from our perspective, unfolding over years and centuries as the ejected material spreads out. But from the star's perspective, it's instantaneous. One moment it's a star, the next, it's an expanding shell of debris. The moment the star becomes dust is also the moment those atoms become available for new stars, new planets, new possibilities. The dust and gas will drift through space, cooling, mixing with the interstellar medium. Over millions of years, some of it will collapse under gravity, forming new stars. The moment the star becomes dust is an ending and a beginning, the star's death, but also the birth of countless futures built from its remains. The formation of neutron stars and black holes. Not all of the star is destroyed. The formation of neutron stars and black holes happens in the core. When the core collapses, if its mass is between about 1.4 and 3 solar masses, it becomes a neutron star, a sphere of neutrons packed so densely that a teaspoon weighs billions of tons. Neutron stars are incredibly compact, about 20 kilometers across, but containing more mass than the Sun. If the core is more massive, even neutron degeneracy pressure can't support it. The core continues collapsing, forming a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. The formation of neutron stars and black holes is the ultimate fate of massive stellar cores. These objects are among the most extreme in the universe, laboratories for physics at its limits. The formation of neutron stars and black holes from supernovae is how the universe produces these exotic objects, creating them in the violent aftermath of stellar death. They're remnants, but they're also beginnings. Neutron stars can become pulsars, black holes can grow by accretion. The two paths of a star's death. Not all supernovae are the same. The two paths of a star's death depend on the star's mass and composition. Massive stars, those with more than 8 solar masses, die in core collapse supernovae. Their cores run out of fuel, collapse, and trigger an explosion that tears the star apart. But there's another path. White dwarfs, the remnants of lower mass stars, can also explode as supernovae under the right conditions. If a white dwarf in a binary system accretes matter from its companion, it can grow until it reaches the Chandrasekhar limit. At that point, carbon fusion ignites throughout the star simultaneously, and the entire white dwarf explodes. This is a type Ia supernovae. The two paths of a star's death produce different explosions with different characteristics. Core collapse supernovae are messy, variable, and leave behind remnants. Type Ia supernovae are uniform, predictable, and leave nothing behind. The entire star is destroyed. The two paths of a star's death reflect the diversity of stellar evolution, showing that endings come in multiple forms. The core collapse supernova. This is the classic supernova, the death of a massive star. The core collapse supernova begins when the star's core runs out of fuel and collapses under its own gravity. The collapse triggers a rebound, a shock wave that tears through the star's outer layers, causing them to explode. The core collapse supernova is caused by the loss of pressure support in the core. Without fusion to generate outward pressure, gravity wins. The core collapses from the size of Earth to the size of a city in less than a second. The collapse releases enormous gravitational energy, mostly as neutrinos. The shock wave, powered by a fraction of that energy, drives the explosion. The core collapse supernova leaves behind a remnant, a neutron star or black hole. The explosion ejects the star's outer layers into space, enriching the interstellar medium with heavy elements. The core collapse supernova is nature's recycling program, the mechanism by which massive stars return their material to the cosmos, enabling future generations of stars and planets to form. The type Ia supernova, a different kind of end. Some supernovae don't come from massive stars. The type Ia supernova is a different kind of end, involving white dwarfs rather than massive stars. A white dwarf is the remnant of a star like the Sun, a dense, Earth-sized object composed of carbon and oxygen, no longer undergoing fusion. If a white dwarf is in a binary system with another star, it can accrete matter from its companion. As the white dwarf gains mass, it approaches the Chandrasekhar limit, about 1.4 solar masses. When it reaches this limit, the pressure and temperature in its core trigger runaway carbon fusion. The entire white dwarf ignites, fusing carbon into heavier elements in a thermonuclear explosion. The type I supernova is different from a core collapse supernova in several ways. It's caused by fusion, not collapse. It destroys the entire star. There's no remnant, and most importantly, type I supernovae are remarkably uniform in their peak brightness, making them valuable as standard candles for measuring cosmic distances. The binary star that steals its partner's life. Binary stars are common in the universe. The binary star that steals its partner's life is a system where a white dwarf accretes matter from a companion. If the companion is a red giant or another evolved star, the white dwarf's gravity can pull gas from its outer layers. This process is slow, taking millions of years, but eventually, the white dwarf accumulates enough mass to reach the Chandrasekhar limit. The binary star that steals its partner's life is a slow murder. The white dwarf grows heavier, its core denser, until finally it reaches critical mass. Carbon fusion ignites. The white dwarf explodes. The companion survives, now orbiting alone, its partner transformed into an expanding cloud of gas. The binary star that steals its partner's life is a reminder that not all stellar deaths are solitary. Many stars exist in pairs or groups, and interactions between stars can lead to outcomes that wouldn't happen to isolated stars. The binary system creates conditions for a type Ia supernova, a different path to explosion. The white dwarf that couldn't stop feeding. In a binary system, a white dwarf can accrete matter from its companion. The white dwarf that couldn't stop feeding grows heavier over time. Hydrogen from the companion falls onto the white dwarf's surface, where it fuses in brief bursts, called novae. But some of the accreted material remains, adding to the white dwarf's mass. The white dwarf that couldn't stop feeding inches closer to the Chandrasekhar limit. There's no turning back. The accretion continues, driven by orbital dynamics and the companion's evolution. Eventually, the white dwarf reaches critical mass. Its core compresses, temperature rises, carbon fusion begins. The white dwarf that couldn't stop feeding has sealed its fate. The fusion ignites throughout the star in a runaway thermonuclear reaction. The entire white dwarf explodes in a Type Ia supernova. The white dwarf that couldn't stop feeding illustrates a fundamental principle. Even small, steady changes can lead to catastrophic outcomes. Slowly, patiently, the white dwarf accumulated mass until it could no longer support itself. Then, in an instant, it was destroyed. The critical mass that sparks destruction. Mass matters in stellar physics. The critical mass that sparks destruction is about 1.4 solar masses, known as the Chandrasekhar limit. This is the maximum mass a white dwarf can support through electron degeneracy pressure. When a white dwarf reaches this limit, either through accretion or merger with another white dwarf, its fate is sealed. The critical mass that sparks destruction is reached when the core's density and temperature become high enough for carbon fusion to ignite. In a normal star, fusion occurs in the core and proceeds gradually, but in a white dwarf at the Chandrasekhar limit, the conditions are different. When carbon fusion ignites, it does so throughout the star almost simultaneously. The reaction is runaway. Fusion heats the star, heating accelerates fusion, and within seconds, the entire white dwarf is consumed. The critical mass that sparks destruction is a threshold, a point of no return. Below it, the white dwarf is stable, cooling slowly over billions of years. Above it, explosion is inevitable. The critical mass is nature's trigger, the precise point where stability ends and catastrophe begins. The thermonuclear explosion of perfection. Type Ia supernovae are remarkably uniform. The thermonuclear explosion of perfection occurs because the conditions are nearly identical in every case. A white dwarf reaches the Chandrasekhar limit. Carbon fusion ignites. The star explodes. Because the mass is always the same, about 1.4 solar masses, and the composition is similar, carbon and oxygen. The explosions produce similar amounts of energy and similar peak brightnesses. The thermonuclear explosion of perfection makes Type Ia supernovae incredibly useful. Astronomers can use them as standard candles, objects of known brightness. By measuring how bright they appear and comparing to their actual brightness, we can calculate their distance. The thermonuclear explosion of perfection is surprisingly consistent across the universe. Whether it happens in a nearby galaxy or billions of light years away, a Type Ia supernova peaks at roughly the same luminosity. This consistency has been crucial for cosmology, allowing astronomers to map the expansion of the universe with unprecedented precision. The thermonuclear explosion of perfection is nature's gift to astronomers, a reliable, repeatable explosion that serves as a cosmic measuring stick. The cosmic standard candle. In astronomy, a standard candle is an object with known luminosity. The cosmic standard candle for measuring vast distances is the Type Ia supernova. Because these explosions are so uniform, astronomers can use them to calculate distances to faraway galaxies. The cosmic standard candle works through a simple principle. If you know an object's intrinsic brightness and you measure how bright it appears, you can calculate how far away it is. Type Ia supernova always peak at about the same intrinsic brightness, making them ideal standard candles. The cosmic standard candle has been used to map the universe's expansion. By observing Type Ia supernova in distant galaxies, astronomers measure how fast those galaxies are moving away from us. These measurements revealed one of the most surprising discoveries in modern cosmology. the universe's expansion is accelerating, driven by something called dark energy. The cosmic standard candle transformed our understanding of the cosmos. Without type Ia supernovae, we might not know that dark energy exists, or that the universe's expansion is speeding up. The supernova that measures the universe. Distance measurements in cosmology are challenging. The supernova that measures the universe is the type I supernova, used as a standard candle to gauge cosmic distances. In the 1990s, two independent teams of astronomers used type I supernova to measure the expansion history of the universe. They observed supernova in distant galaxies, measuring their brightness and redshift. The supernova that measures the universe revealed something unexpected. Distant supernova appeared dimmer than predicted, suggesting they were farther away than expected. This meant the universe's expansion wasn't slowing down as anticipated. It was speeding up. The supernova that measures the universe led to the discovery of dark energy, a mysterious force causing the universe's accelerated expansion. This discovery earned the 2011 Nobel Prize in Physics. The supernova that measures the universe shows how single astronomical phenomena can revolutionize our understanding of cosmology. By observing stellar explosions billions of light years away, we learned that the universe is not only expanding, but accelerating, driven by an unknown energy that makes up most of the cosmos. The discovery that changed cosmology. In 1998, two teams announced their findings. The discovery that changed cosmology was that the universe's expansion is accelerating. Both teams had been studying distant type of supernovae, using them as standard candles to measure cosmic expansion. They expected to find that expansion was slowing due to gravity. Instead, they found the opposite. The discovery that changed cosmology meant that some unknown force, later called dark energy, was causing expansion to accelerate. This was completely unexpected. Dark energy makes up about 68% of the universe's total energy, yet we don't know what it is. The discovery that changed cosmology transformed our understanding of the universe's fate. If expansion continues to accelerate, galaxies will move apart faster and faster. Eventually, even nearby galaxies will recede beyond the cosmic horizon. The discovery that changed cosmology was made possible by supernovae, by dying stars billions of light years away, by explosions that occurred when the universe was younger. It's a testament to how observing distant events can reveal fundamental truths about the cosmos. The evidence of dark energy in their light. Dark energy is invisible, but its effects are not. The evidence of dark energy in their light comes from observations of distant type is supernovae. These supernovae appear dimmer than they should. If the universe's expansion were slowing, the dimness means they're farther away than expected, which means space has expanded more than predicted. The evidence of dark energy in their light is indirect, but compelling. Something is causing the universe's expansion to accelerate, and the best explanation is dark energy, a form of energy that permeates space itself. The evidence of dark energy in their light has been confirmed by multiple independent observations, including measurements of the cosmic microwave background and large-scale structure. The evidence of dark energy in their light tells us that most of the universe is made of something we don't understand. Dark energy doesn't interact with light or matter in any known way, except through its gravitational effect on cosmic expansion. The evidence of dark energy in their light is one of the biggest mysteries in physics, revealed by studying exploding stars. The expanding universe seen in explosions. The universe is expanding, and supernovae help us see it. The expanding universe seen in explosions is revealed through redshift measurements. When a galaxy moves away from us, its light is stretched to longer wavelengths, redshifted. By measuring the redshift of supernovae in distant galaxies, astronomers can determine how fast those galaxies are receding. The expanding universe seen in explosions shows that more distant galaxies are moving away faster, consistent with an expanding universe. But the observations go further. By comparing distances and recession velocities of supernovae at different cosmic epochs, astronomers can reconstruct the universe's expansion history. The expanding universe seen in explosions revealed that expansion hasn't been constant, it's been accelerating. This acceleration began about 5 billion years ago, when dark energy's influence started dominating over matter's gravitational attraction. The expanding universe seen in explosions is a dynamic picture showing how cosmic expansion has evolved over time. Supernovae provide snapshots of this evolution, allowing us to piece together the universe's past and predict its future. The patterns hidden in distant supernovae. Observing distant supernovae reveals patterns in cosmic history. The patterns hidden in distant supernovae include the relationship between brightness, distance, and redshift. By studying many supernovae at various distances, astronomers map the universe's expansion. The patterns hidden in distant supernovae show that expansion has accelerated over time. Close supernovae follow one pattern, distant supernovae another. The difference reveals when dark energy became dominant. The patterns hidden in distant supernovae also reveal information about the universe's composition. By comparing observations to theoretical models, astronomers constrain the amounts of dark energy, dark matter, and ordinary matter. The patterns hidden in distant supernovae are subtle, requiring careful observations and analysis. Dust can dim light, intrinsic variations can introduce uncertainty, and measuring distances across billions of light years is challenging. But by observing many supernovae and averaging out random variations, clear patterns emerge. The patterns hidden in distant supernovae have transformed cosmology, turning it from a largely theoretical field into an observational science with precise measurements of cosmic parameters. The names and classifications we use. Supernovae are classified by their spectra. The names and classifications we use distinguish different types based on the elements visible in their light. Type I supernovae lack hydrogen lines in their spectra. Type Ia supernovae show strong hydrogen lines. Within type I, there are subdivisions. Type I supernovae show strong silicon lines and are thermonuclear explosions of white dwarfs. Type Ib and I supernovae lack silicon and result from core collapse of massive stars that lost their outer hydrogen Eb or hydrogen and helium IC layers. The names and classifications we use help astronomers understand what kind of star exploded and what caused the explosion. Type II supernovae are subdivided based on their light curves and spectra. Type IIp have plateau light curves. Type IIl decline linearly, and Type IIb show characteristics of both hydrogen-rich and hydrogen-poor supernovae. The names and classifications we use are based on observable characteristics, not always on underlying physics, which can sometimes be confusing. A Type IIa supernovae is fundamentally different from types Ib and Ic, despite the similar naming. The names and classifications we use continue to evolve as we discover new types of explosions and refine our understanding of stellar deaths. The naming system reflects astronomy's history. Classifications were made before mechanisms were understood, and we're still using those historical categories today. The Type II supernova and its hydrogen signature. The most common supernova from massive stars shows hydrogen. The Type II supernova and its hydrogen signature result from stars that retain their outer hydrogen envelopes until death. When the core collapses and the shock wave propagates outward, it plows through these hydrogen-rich layers. The hydrogen, heated by the shock wave, glows intensely, producing the characteristic spectral lines that identify a Type II supernova. The Type II supernova and its hydrogen signature tell us about the star's structure before it exploded. Stars that retain their hydrogen envelopes are typically red supergiants, massive stars that have evolved off the main sequence, but haven't lost their outer layers to stellar winds or binary interactions. The Type II supernova and its hydrogen signature dominates the plateau in the light curve, the phase where brightness remains relatively constant for weeks. This plateau occurs because hydrogen recombination releases energy gradually, maintaining the supernova's brightness. The Type II supernova and its hydrogen signature is the most straightforward massive star death. A star lives, evolves, and explodes with its layers intact. The spectra that reveal their secrets. Light carries information. The spectra that reveal their secrets are obtained by splitting supernova light into its component wavelengths. Each element produces characteristic lines in the spectrum, bright emission lines or dark absorption lines, at specific wavelengths. By analyzing these lines, astronomers can identify which elements are present in the explosion. The spectra that reveal their secrets show hydrogen in Type II supernovae, silicon in Type Ia, and lack of hydrogen in types Ob and Ic. The spectra that reveal their secrets also show the explosion's velocity. Spectral lines are shifted by the Doppler effect, revealing how fast material is moving. Material moving toward us appears blue shifted. Material moving away appears red shifted. The spectra that reveal their secrets change over time as the explosion evolves. Early spectra show the outer layers. Later spectra reveal deeper layers as the expanding gas becomes transparent. The spectra that reveal their secrets are like fingerprints, unique to each explosion, yet following patterns that allow classification and understanding. The astronomers who watch the sky burn. Discovering supernovae requires vigilance. The astronomers who watch the sky burn scan the heavens regularly, looking for new lights in familiar galaxies. Before automation, this was done by eye, comparing photographs taken weeks or months apart. Today, automated surveys scan thousands of galaxies nightly, using computer algorithms to identify new transients. The astronomers who watch the sky burn work around the clock, following up discoveries with spectroscopy and photometry, measuring light curves and spectra to classify and study each supernova. The astronomers who watch the sky burn are spread across the globe, part of a coordinated network, ensuring that no event goes unobserved. When a bright supernova appears, alerts go out to observatories worldwide. Telescopes turn toward the explosion, gathering data across the electromagnetic spectrum. The astronomers who watch the sky burn are modern sentinels, monitoring the universe's violent events, documenting stellar deaths, and extracting knowledge from destruction. Their work has revolutionized our understanding of stellar evolution, cosmic distances, and the universe's expansion. The ancient records of guest stars. Long before modern astronomy, people noticed new stars appearing in the sky. The ancient records of guest stars include observations from Chinese, Korean, Japanese, and Arab astronomers, who meticulously documented celestial events. These guest stars were what we now call supernovae, stellar explosions, bright enough to be visible to the naked eye. The ancient records of guest stars are invaluable. They tell us when and where historical supernovae occurred, allowing modern astronomers to identify their remnants. The ancient records of guest stars describe brightness, duration, and sometimes color. Some were visible in daylight. Others lasted for months before fading. The ancient records of guest stars include the supernovae of 1006, the brightest in recorded history, the supernovae of 1054, which created the Crab Nebula, Tycho's supernovae in 1572, and Kepler's in 1604. These observations, made centuries ago without telescopes, provide historical context for understanding how supernovae evolve. The ancient records of guest stars connect us to our ancestors, who watched the same sky and wondered about the same transient lights. The Chinese astronomers, who saw the Crab In 1054 CE, Chinese astronomers recorded a brilliant new star. The Chinese astronomers who saw the crab documented a guest star in the constellation corresponding to modern-day Taurus. It was visible for 23 days in daylight and remained visible at night for nearly 2 years. The Chinese astronomers who saw the crab didn't know they were witnessing a supernova. They recorded it as one of many celestial phenomena, part of their systematic sky monitoring. The Chinese astronomers who saw the crab left detailed records that modern astronomers use to identify the event with the Crab Nebula, the expanding remnant of that explosion. By comparing the position described in historical texts with the nebula's location, and by measuring the nebula's expansion rate and working backward, astronomers confirmed that the Crab Nebula was created by the 1054 supernova. The Chinese astronomers who saw the crab provided a crucial link between history and modern astronomy, allowing us to study a supernova remnant with known age and origin. The supernova of 1054, nearly 1,000 years ago, a massive star in our galaxy exploded. The supernova of 1054 occurred about 6,500 light-years from Earth in the constellation Taurus. At its peak, it was one of the brightest objects in the night sky, visible in daylight for weeks. The supernova of 1054 was observed and recorded by astronomers in China, Japan, and the Arab world. In Europe, there are fewer records, possibly due to political turmoil or cloudy weather, though some researchers claim references exist. The supernova of 1054 gradually faded over months, eventually disappearing from view. Its location was forgotten until the 18th century, when astronomers discovered a nebula in that part of the sky. In the 1920s, measurements showed the nebula was expanding, and calculations of its expansion rate traced it back to an explosion around 1054. The supernova of 1054 was confirmed as the source of the Crab Nebula, one of the most studied objects in astronomy. The supernova of 1054 left behind a rapidly spinning neutron star, a pulsar still visible today. The birth of the Crab Nebula. The explosion that Chinese astronomers saw in 1054 created a nebula. The birth of the Crab Nebula was the moment when the star's outer layers, blown into space by the supernova, began expanding outward. Over centuries, this expanding gas formed the structure we see today, a complex, filamentary nebula glowing across the electromagnetic spectrum. The birth of the Crab Nebula continues today. The nebula is still expanding, growing larger over time. Observations decades apart show measurable changes in its size and structure. The birth of the Crab Nebula is powered by the pulsar at its center, a rapidly spinning neutron star that emits beams of radiation. The pulsar's energy drives the nebula's glow, heating the gas and accelerating particles to relativistic speeds. The birth of the Crab Nebula has been ongoing for nearly a millennium, and it will continue for millennia more before the expanding gas dissipates into the interstellar medium. The birth of the Crab Nebula is a slow-motion transformation, stellar death becoming cosmic art. The pulsar left behind, at the heart of the Crab Nebula, spins a remnant. The pulsar left behind is a neutron star, the collapsed core of the massive star that exploded in 1054. It spins about 30 times per second, emitting beams of radiation from its magnetic poles. As it rotates, these beams sweep across space like a lighthouse, and when they point toward Earth, we detect pulses. The pulsar left behind was discovered in 1968, confirming that the Crab Nebula's central star was indeed a neutron star. The pulsar left behind is young by cosmic standards, less than 1,000 years old, and it's still slowing down. The rotation rate decreases gradually as the pulsar loses energy. That energy doesn't disappear. It powers the nebula, creating the synchrotron radiation that makes the crab glow. The pulsar left behind is one of the most studied objects in astronomy, a laboratory for understanding neutron stars, pulsars, and high-energy astrophysics. The pulsar left behind is the star's final form, a compact remnant that will persist for billions of years. The light that reached medieval Earth. When light from the 1054 supernova reached Earth, the world was very different. The light that reached medieval Earth arrived during a time of castles, knights, and feudal societies. In China, the Song dynasty recorded celestial events meticulously. In Europe, the medieval period was marked by limited scientific observation. The light that reached medieval Earth had been traveling for 6,500 years, crossing the void between stars. The light that reached medieval Earth carried information about a star that had actually exploded millennia earlier, in what we now call the Bronze Age. By the time humans saw it, the event was ancient history. But the light was just arriving. The light that reached medieval Earth was witnessed by people who had no understanding of stars, distances, or explosions. They saw a transient light and recorded it as a celestial omen or curiosity. The light that reached medieval Earth connects us to those ancient observers, showing that while technology advances, the sky we watch is the same sky they wondered about. The 1987, a supernova in the Large Magellanic Cloud. In February 1987, astronomers detected a new supernova, the 1987. A supernova in the Large Magellanic Cloud was the brightest supernova visible from Earth since 1604. It occurred in a small satellite galaxy of the Milky Way, about 160,000 light-years away. The 1987, a supernova in the Large Magellanic Cloud, was discovered by observers in the southern hemisphere and quickly became one of the most studied supernovae in history. For the first time, astronomers had modern instruments to observe a nearby supernova. The 1987, a supernova in the Large Magellanic Cloud, was unusual. The progenitor star was identified in archival images, a blue supergiant, not the expected red supergiant. This challenged existing models of massive star evolution. The 1987, a supernova in the Large Magellanic Cloud, provided unprecedented data. Observations across the spectrum revealed details of the explosion, the expanding shockwave, and the formation of elements. The 1987, a supernova in the Large Magellanic Cloud, continues to be studied today, over 3 decades later, as the expanding remnant interacts with surrounding material and evolves in observable ways. The neutrinos detected for the first time. Supernova 1987. A made history in multiple ways. The neutrinos detected for the first time from a supernova arrived on February 23, 1987, hours before the optical light was seen. 2 neutrino detectors, Kamiokanda II in Japan and IMB in the United States, recorded a burst of neutrinos, about 2 dozen total. The neutrinos detected for the first time confirmed theoretical predictions about core collapse supernova. When the star's core collapses, it releases most of its energy as neutrinos, which barely interact with matter and escape immediately. The optical explosion comes later, when the shock wave reaches the star's surface. The neutrinos detected for the first time provided direct evidence of the core collapse, confirming that neutrino emission is the primary energy release mechanism. The neutrinos detected for the first time also validated the detectors themselves, proving they could capture these elusive particles. The neutrinos detected for the first time opened a new window on stellar death, showing that neutrino astronomy is possible and valuable for understanding supernovae. The confirmation of stellar death in real time. Supernova 1987 A was observed from beginning to end. The confirmation of stellar death in real time happened as astronomers watched the explosion evolve. The progenitor star, a blue supergiant called Sandu Lake, -69 degrees 202, disappeared from the sky. In its place, a brilliant point of light appeared, brightening over days, then fading over months. The confirmation of stellar death in real time included observing the light curve, which showed characteristic peaks and declines as the explosion cooled and radioactive elements decayed. The confirmation of stellar death in real time included spectroscopy, revealing the presence of heavy elements forged in the explosion. The confirmation of stellar death in real time included the detection of gamma rays from radioactive cobalt-56, proving that nuclear reactions occurred during the explosion. The confirmation of stellar death in real time was a triumph for astrophysics, validating decades of theoretical work about how massive stars die. Everything predicted was observed: neutrinos, light curve shape, spectral evolution, element formation. The confirmation of stellar death in real time turned supernova theory into observational fact. The rings of light still expanding today. Around supernova 1987 A, there are rings. The rings of light still expanding today were created before the explosion, when the progenitor star shed material in its final evolutionary stages. The rings of light still expanding today are illuminated by the supernova's radiation. As the shock wave from the explosion travels outward, it eventually reaches these rings, heating them and causing them to glow. The rings of light still expanding today are being monitored by telescopes, including Hubble. Over decades, astronomers have watched the shock wave interact with the rings, creating bright spots called hot spots, where the collision is most intense. The rings of light still expanding today provide a three-dimensional view of the explosion and its environment. The rings are tilted relative to our line of sight, allowing astronomers to study the explosion's geometry. The rings of light still expanding today are beautiful, glowing structures that will eventually fade as the shock wave passes and the energy dissipates. They're a transient structure, a brief phase in the supernova remnant's evolution. The cosmic laboratories of element creation. Supernovae are where heavy elements are made. The cosmic laboratories of element creation forge atoms that couldn't form anywhere else. In a star's core during its lifetime, fusion creates elements up to iron, but elements heavier than iron require different conditions. The cosmic laboratories of element creation provide those conditions during the explosion. The intense heat and neutron flux in a supernova allow rapid neutron capture, where atomic nuclei absorb multiple neutrons before they can decay. This raw process creates elements like gold, platinum, lead, and uranium. The cosmic laboratories of element creation scatter these elements into space, enriching the interstellar medium. Over time, this enriched gas collapses to form new stars and planets. The cosmic laboratories of element creation are why the universe is chemically diverse. Without supernovae, there would be no heavy elements, no rocky planets, no complex chemistry. The cosmic laboratories of element creation connect stellar death to planetary birth, showing how destruction enables creation on cosmic scales. The gold and silver born from explosions. Every piece of gold you've ever seen came from a supernova. The gold and silver born from explosions were forged in the intense conditions of stellar death. When a massive star explodes, or when two neutron stars collide, the extreme temperatures and neutron densities allow heavy elements to form. The gold and silver born from explosions are products of the raw process, rapid neutron capture, that builds up atomic nuclei into the heaviest stable elements. The gold and silver born from explosions are scattered into space by the explosion, mixing with interstellar gas. Billions of years later, some of that material became part of our solar system. The gold and jewelry, the silver and electronics, the platinum and catalytic converters, all were created in stellar explosions. The gold and silver born from explosions traveled across space and time to become part of Earth. They're stardust, literally, atoms forged in the most violent events in the universe. The gold and silver born from explosions connect us directly to supernovae, reminders that we're made of stars. The iron in our blood, forged in their hearts. Iron is essential for life. The iron in our blood forged in their hearts came from massive stars. During a star's lifetime, fusion in its core creates elements up to iron. Iron is the endpoint of fusion. Fusing iron doesn't release energy, so fusion stops there. When the star explodes, that iron is scattered into space. The iron in our blood forged in their hearts eventually became part of the molecular cloud that formed our solar system. Some became part of Earth. Some was incorporated into living organisms. The iron in hemoglobin, which carries oxygen through your blood, was created in a star's core billions of years ago. The iron in our blood forged in their hearts connects every breath you take to stellar nucleosynthesis. The iron in our blood forged in their hearts is ancient, cosmic, recycled stellar material. Every heartbeat is powered by atoms created in stellar furnaces. The iron in our blood forged in their hearts is a tangible link between human biology and cosmic history, showing that we're not separate from the universe, but made of it. The stardust that builds planets. Planets form from the debris of dead stars. The stardust that builds planets is the gas and dust enriched by supernovae. When the interstellar medium, seeded with heavy elements, collapses under gravity, it forms new stars and planetary systems. The stardust that builds planets includes all the elements necessary for rocky planets: silicon, iron, magnesium, oxygen. The stardust that builds planets came from countless supernovae over billions of years, gradually enriching the galaxy. Later generations, born from gas enriched by supernovae, contained heavier elements. The stardust that builds planets made Earth possible. Without supernovae, there would be no rock, no metal, no chemistry beyond the simplest molecules. The stardust that builds planets is why we exist. Our planet, our bodies, everything around us is made of material created in stars and scattered by explosions. The stardust that builds planets is the ultimate recycling program, the universe reusing material, transforming destruction into creation, ensuring that nothing is ever truly lost. The role of supernovae in galactic evolution. Supernovae shape galaxies. The role of supernovae in galactic evolution includes injecting energy into the interstellar medium, creating bubbles and shells of hot gas, driving galactic winds, and regulating star formation. The role of supernovae in galactic evolution is both destructive and creative. Explosions disrupt gas clouds, preventing them from collapsing, slowing star formation. But shockwaves also compress gas, triggering new star formation. The role of supernovae in galactic evolution includes chemical enrichment, gradually increasing the abundance of heavy elements in the galaxy. The role of supernovae in galactic evolution affects the galaxy's structure. Explosions and spiral arms can create holes in the gas distribution, alter the arm's shape, and drive material out of the galactic plane. The role of supernovae in galactic evolution is ongoing. Every supernovae adds energy and matter to the galaxy, contributing to its evolution. The role of supernovae in galactic evolution is so significant that models of galaxy formation must include supernovae to accurately reproduce observed galactic properties. The shockwaves that trigger new stars. Supernova shockwaves don't just destroy, they create. The shockwaves that trigger new stars compress nearby gas clouds, increasing their density. If the compression is strong enough, gravity takes over, and the cloud collapses to form new stars. The shockwaves that trigger new stars are a form of triggered star formation, where one generation of stars influences the next. Massive stars live fast, die young, and their supernova trigger the formation of new stars from the same molecular cloud that formed them. The shockwaves that trigger new stars create a cycle. Stars form, some go supernova. Those supernova trigger more star formation. The shockwaves that trigger new stars are visible in observations of star-forming regions, where expanding supernova remnants are surrounded by areas of active star formation. The shockwaves that trigger new stars are part of galactic ecology, the complex web of processes that regulate when and where stars form. The shock waves that trigger new stars ensure that stellar death leads to stellar birth, continuing the cycle that has been ongoing for billions of years. The recycling of matter across eons. The universe recycles everything. The recycling of matter across eons is driven largely by supernovae. Stars form from gas clouds. They fuse hydrogen into helium and heavier elements. Eventually, they return that material to space, gently through stellar winds or violently through supernovae. The recycling of matter across eons enriches the interstellar medium with heavy elements. Each generation of stars contains more heavy elements than the last. The recycling of matter across eons means that the atoms in your body have been through multiple stars. They've been fused, scattered, reformed, scattered again. The recycling of matter across eons operates on timescales of billions of years, but it's continuous, ongoing, essential. Without recycling, all matter would be locked in stars or stellar remnants. The recycling of matter across eons keeps the universe dynamic, ensures that new stars and planets continue to form, and creates the chemical diversity necessary for complex structures like planets and life. The recycling of matter across eons is the universe's fundamental process, the mechanism by which it evolves and changes. The sculpting of interstellar clouds. Supernova shockwaves carve through space. The sculpting of interstellar clouds happens as these shockwaves plow through gas and dust, compressing some regions, dispersing others. The sculpting of interstellar clouds creates structure, filaments, shells, bubbles, in the otherwise smooth interstellar medium. The sculpting of interstellar clouds affects where future stars will form. Dense, compressed regions are more likely to collapse under gravity. The sculpting of interstellar clouds is visible in images of star-forming regions, where expanding bubbles of hot gas surround young star clusters. Blown by stellar winds and supernova explosions, the sculpting of interstellar clouds is an ongoing process. As long as stars form and die, they'll continue shaping their environment. The sculpting of interstellar clouds is part of the feedback loop between stars and their surroundings. Stars form from clouds, then reshape those clouds through their energy output, influencing where the next generation forms. The sculpting of interstellar clouds is architecture on galactic scales, stars building structures in gas that will one day birth new stars. The bubbles of hot gas in galactic arms. Look at images of spiral galaxies, and you'll see bubbles. The bubbles of hot gas in galactic arms are created by stellar winds and supernovae from massive stars. These stars live in clusters, often in spiral arms, where star formation is active. When they explode, their combined energy creates superbulls, vast cavities of hot, low-density gas, surrounded by shells of compressed cooler gas. The bubbles of hot gas in galactic arms can be hundreds of light years across. They glow in X-rays, visible to space-based X-ray telescopes. The bubbles of hot gas in galactic arms are temporary structures, lasting millions of years before dissipating. The bubbles of hot gas in galactic arms affect star formation. The compressed shells can trigger new star formation, continuing the cycle. The bubbles of hot gas in galactic arms are evidence of stellar feedback, the way stars affect their environment. The bubbles of hot gas in galactic arms show that galaxies aren't static. They're dynamic, shaped by the energy output of their stars, constantly changing, evolving in response to stellar life and death. The energy that shapes the Milky Way. Our galaxy is shaped by its stars. The energy that shapes the Milky Way comes partly from supernovae. Over billions of years, countless supernovae have exploded, each one releasing enormous energy into the galactic environment. The energy that shapes the Milky Way drives galactic winds, flows of hot gas out of the galactic disk into the halo. The energy that shapes the Milky Way regulates star formation, preventing the galaxy from converting all its gas into stars too quickly. The energy that shapes the Milky Way creates the hot, diffuse medium that fills the space between stars. The energy that shapes the Milky Way affects the galaxy's structure, maintaining the disk's thickness, influencing spiral arm formation, and possibly contributing to the central bar. The energy that shapes the Milky Way is ongoing. Every supernova adds energy to the system. The energy that shapes the Milky Way is balanced by cooling, as gas radiates energy and cools, allowing new star formation. This balance between heating and cooling, driven largely by supernovae, maintains the galaxy in a quasi-equilibrium state. The evidence of past supernovae in Earth's rocks. Supernovae leave traces. The evidence of past supernovae in Earth's rocks comes in the form of radioactive isotopes that don't occur naturally on Earth. These isotopes are created in supernovae and can only reach Earth if a supernova occurs relatively nearby. The evidence of past supernovae in Earth's rocks includes iron-60, a radioactive isotope of iron with a half-life of 2.6 million years. Iron-60 doesn't form on Earth. It's created in supernovae. Finding it in deep-sea sediments and Antarctic snow suggests that Earth has been bathed in supernova debris in the relatively recent past. The evidence of past supernova in Earth's rocks indicates that a supernova occurred within a few hundred light-years of Earth, sometime in the last few million years. The evidence of past supernova in Earth's rocks is exciting because it connects cosmic events to Earth's history. Did these supernova affect Earth's climate or life? We don't know yet, but the evidence shows that Earth is not isolated from cosmic violence. The iron-60 found in ocean sediments. In the 1990s, scientists discovered something unexpected. The iron-60 found in ocean sediments shouldn't be there. Iron-60 is radioactive, decaying with a half-life of 2.6 million years. It's not produced on Earth. The only way it can reach Earth is through supernova debris. The iron-60 found in ocean sediments was deposited about 2 to 3 million years ago. Based on the depth at which it was found and geological dating, the iron-60 found in ocean sediments has also been discovered in Antarctic snow and lunar samples. The iron-60 found in ocean sediments indicates that Earth passed through a cloud of supernova debris. The supernova likely occurred within 100 to 300 light-years, close enough for the debris to reach our solar system. The iron-60 found in ocean sediments is a cosmic fingerprint, evidence that we live in an active, dynamic galaxy where supernova occasionally occur near enough to leave traces. The iron-60 found in ocean sediments has sparked research into whether the supernova had any effects on Earth's climate or biosphere. The traces of explosions near our solar system. The iron-60 in ocean sediments isn't the only clue. The traces of explosions near our solar system include other isotopes and possibly effects on Earth's atmosphere. The traces of explosions near our solar system suggest that a supernova occurred in what's called the local bubble, a region of low-density hot gas surrounding the solar system. The traces of explosions near our solar system are being studied to determine how close the supernova was, when exactly it occurred, and whether it had any measurable effects on Earth. The traces of explosions near our solar system are evidence that cosmic events can directly impact Earth. While a supernova 100 light-years away isn't dangerous, it can increase cosmic ray flux, potentially affecting cloud formation and climate. The traces of explosions near our solar system remind us that Earth is part of a larger cosmic environment, influenced by events happening far beyond our planet. The traces of explosions near our solar system are written in geological records, waiting to be read and interpreted. The possibility of a nearby supernova long ago. Based on the iron-60 evidence, astronomers have searched for the culprit. The possibility of a nearby supernova long ago has led to investigations of stellar populations near the solar system. Which stars could have gone supernova 2 to 3 million years ago? The possibility of a nearby supernova long ago points to stars that were once part of nearby moving groups or clusters, now dispersed. The possibility of a nearby supernova long ago includes the Scorpius-Centaurus Association, a nearby region of young massive stars. Some of these stars have already gone supernova, and more will in the future. The possibility of a nearby supernova long ago has implications for understanding supernova rates in the galaxy and for assessing risks to Earth. The possibility of a nearby supernova long ago is being studied through multiple approaches, identifying candidate progenitor stars, modeling the local bubbles formation, and searching for additional isotopic evidence. The possibility of a nearby supernova long ago connects human history, albeit deep prehistory, to cosmic events, showing that Earth's environment is influenced by the galaxy around it. The effects of supernova radiation on life. A supernova close to Earth could be dangerous. The effects of supernova radiation on life depend on distance. A supernova within 10 light-years would be catastrophic, bathing Earth in lethal radiation. Between 10 and 50 light-years, effects would be significant, but not necessarily extinction level. The effects of supernova radiation on life include increased cosmic rays, which could deplete Earth's ozone layer, increasing surface UV radiation. The effects of supernova radiation on life might include climate changes from altered atmospheric chemistry. The effects of supernova radiation on life are speculative. We haven't directly observed them, but models suggest that nearby supernovae could cause mass extinctions or at least stress ecosystems. The effects of supernova radiation on life have been proposed as explanations for some mass extinctions in Earth's history. Though evidence is limited, the effects of supernova radiation on life remind us that Earth's biosphere, while resilient, is not isolated from cosmic threats. Supernova, gamma-ray bursts, and other high-energy events can potentially impact life on Earth. The threat of cosmic rays and gamma bursts. Supernovae produce cosmic rays, high-energy particles accelerated to nearly light speed. The threat of cosmic rays and gamma bursts includes increased radiation at Earth's surface. If the ozone layer is depleted, some supernovae, those from rapidly rotating massive stars, can produce gamma-ray bursts, beams of intense gamma radiation. The threat of cosmic rays and gamma bursts from a gamma-ray burst pointed at Earth could be severe, though fortunately, these events are rare and directional. The threat of cosmic rays and gamma bursts from typical supernovae is lower, but still real. A nearby supernovae would significantly increase cosmic ray flux at Earth, potentially affecting electronics, satellites, and aviation, in addition to biological effects. The threat of cosmic rays and gamma bursts is assessed by astronomers monitoring nearby massive stars. The good news is that no stars close enough to pose a serious threat are expected to go supernova soon. The threat of cosmic rays and gamma bursts is real but distant, one of many cosmic hazards that Earth faces on timescales of millions of years. The distance needed for safety. How far away is safe? The distance needed for safety from a supernova depends on the star's mass and the explosion's energy. Generally, supernovae farther than 50 light-years pose minimal threat to Earth. The distance needed for safety increases. If the supernova produces a gamma-ray burst, then you'd want to be thousands of light-years away. The distance needed for safety is comforting. Most stars capable of going supernova are much farther away. The nearest supernova candidate, Betelgeuse, is about 650 light-years away, well beyond the danger zone. The distance needed for safety means that while supernovae are spectacular and energetic, they're not an imminent threat to Earth. The distance needed for safety is one reason life has survived on Earth for billions of years. Supernovae occur regularly in the galaxy, but most are far enough away that their effects are minimal. The distance needed for safety doesn't mean we're completely protected, but it does mean that supernova-induced extinctions are rare, happening perhaps once in hundreds of millions of years at most. The stars we watch closely today. Some stars are supernova candidates, and astronomers monitor them. The stars we watch closely today include red supergiants, massive stars nearing the end of their lives. These stars are unstable, varying in brightness, losing mass through powerful stellar winds. The stars we watch closely today include Wolf-Rayet stars, even more massive and hotter, having lost their outer layers, burning through their final nuclear fuel. The stars we watch closely today are spread throughout the Milky Way and nearby galaxies. When one goes supernova, we want to be ready. Modern astronomy has alert networks that notify observers worldwide when transients are detected. The stars we watch closely today include objects that might go supernova soon, though soon in astronomical terms could mean any time in the next million years. The stars we watch closely today are studied for signs of instability, changes in brightness or spectrum that might herald an impending explosion. The stars we watch closely today are our best candidates for witnessing a nearby supernova in our lifetimes. The red supergiant Betelgeuse in Orion. Betelgeuse is one of the most famous stars in the sky. The red supergiant Betelgeuse in Orion marks the shoulder of the Hunter, one of the brightest stars visible from Earth. It's massive, about 10 to 20 times the Sun's mass, and enormous, with a radius that would extend past Jupiter's orbit if placed at the Sun's position. The red supergiant Betelgeuse in Orion is a variable star, changing brightness over weeks and months. In late 2019 and early 2020, it dimmed significantly, sparking speculation that it might be about to go supernova. The red supergiant Betelgeuse in Orion returned to normal brightness, but the dimming reminded everyone that this star will explode someday. The red supergiant Betelgeuse in Orion is relatively close, about 650 light-years away. When it goes supernova, it will be the brightest since 1604, visible in daylight, casting shadows at night. The red supergiant Betelgeuse in Orion is a supernova waiting to happen, a celestial time bomb that could go off tomorrow or in 100,000 years. The star that might go supernova soon. Betelgeuse is nearing the end. The star that might go supernova soon has exhausted most of its nuclear fuel and is in the final stages of stellar evolution. It's fusing heavier elements in its core, approaching the point where it will create an iron core and collapse. The star that might go supernova soon could explode anytime, tomorrow, next year, or thousands of years from now. In astronomical terms, soon is relative. The star that might go supernova soon is being closely monitored. Astronomers measure its brightness, study its spectrum, track changes in its size and temperature. Any unusual behavior could signal that the end is near. The star that might go supernova soon will provide an unprecedented opportunity. No supernova has been visible to the naked eye in our galaxy since 1604, before the invention of the telescope. When Betelgeuse explodes, modern instruments will capture every detail. The star that might go supernova soon represents a once-in-a-lifetime event. No one alive has seen a nearby supernova. Betelgeuse could change that, offering a spectacular display and invaluable scientific data. The observations that suggest instability. Betelgeuse's behavior is erratic. The observations that suggest instability include dramatic variations in brightness. In late 2019, Betelgeuse dimmed to less than half its normal brightness, the faintest it had been in recorded history. The observations that suggest instability were later attributed to a dust cloud ejected by the star, blocking our view. But the event showed how unpredictable red supergiants are. The observations that suggest instability include measurements of the star's size. Betelgeuse pulsates, expanding and contracting over periods of months to years. The observations that suggest instability reveal mass loss. Betelgeuse is shedding material through powerful stellar winds, losing mass that will never return. The observations that suggest instability don't necessarily mean imminent explosion, but they show a star in turmoil. The observations that suggest instability remind us that red supergiants are dynamic, complex objects, not stable like the sun. Betelgeuse is in its final phase, and these observations capture a star wrestling with its own instability, approaching the moment when gravity finally wins. The sky that will light up when it happens. When Betelgeuse explodes, the night sky will transform. The sky that will light up when it happens will feature a new star brighter than any planet, rivaling the full moon. The sky that will light up when it happens will show Betelgeuse brightening over hours or days, reaching peak brightness within a week or two, then slowly fading over months. At its brightest, it will cast shadows at night, be visible during the day, and dominate Orion's constellation. The sky that will light up when it happens will be visible from most of Earth. Betelgeuse is far enough south to be seen from mid-northern latitudes and throughout the southern hemisphere. The sky that will light up when it happens will be a global event, witnessed by billions, studied by thousands of astronomers with instruments spanning the electromagnetic spectrum. The sky that will light up when it happens will be beautiful and awe-inspiring, a reminder of the universe's power. The sky that will light up when it happens will eventually fade, returning to normal, but leaving behind memories, photographs, and data that will be analyzed for generations. The future supernovae, waiting in the Milky Way. Betelgeuse isn't alone. The future supernovae, waiting in the Milky Way, include dozens of known massive stars that will explode in the coming millions of years. The future supernovae, waiting in the Milky Way, include red supergiants like Antares and Mu Cephei. They include Wolf-Rayet stars like Gamma Velorum and WR104. The future supernovae, waiting in the Milky Way, are spread throughout the galactic disk, concentrated in spiral arms, where massive stars form. The future supernovae, waiting in the Milky Way, are inevitable. On average, a supernova occurs in the Milky Way every 50 to 100 years, though most are obscured by dust or occur on the far side of the galaxy. The future supernovae waiting in the Milky Way will continue shaping the galaxy, injecting energy and heavy elements, triggering new star formation. The future supernovae waiting in the Milky Way ensure that the galaxy remains dynamic, evolving, alive. The future supernovae waiting in the Milky Way are written in the stars we see today, massive, bright, destined for violent ends. The Wolf-Rayet stars on the edge of collapse. Among the most extreme stars are Wolf-Rayet stars. The Wolf-Rayet stars on the edge of collapse have lost their outer hydrogen envelopes, revealing cores rich in helium, carbon, and oxygen. They're incredibly hot, incredibly luminous, and losing mass at prodigious rates through powerful stellar winds. The Wolf-Rayet stars on the edge of collapse are massive, typically 25 solar masses or more, and they're in the final stages of nuclear burning. The Wolf-Rayet stars on the edge of collapse will explode as supernovae, likely type Ib or IC, lacking hydrogen in their spectra because they've already shed those layers. The Wolf-Rayet stars on the edge of collapse might produce gamma-ray bursts when they explode if they're rotating rapidly and launch relativistic jets. The Wolf-Rayet stars on the edge of collapse are rare. There are only a few hundred known in the Milky Way, but they're important. They represent the most massive stars, the ones that will have the most violent deaths, potentially leaving behind black holes rather than neutron stars. The Wolf-Rayet stars on the edge of collapse are stellar extremes, pushing physics to its limits. The gamma-ray bursts that follow some explosions. Some supernovae produce more than just optical light. The gamma-ray bursts that follow some explosions are the most energetic events in the universe, lasting seconds to minutes. Gamma ray bursts release more energy than the sun will produce in its entire lifetime. The gamma ray bursts that follow some explosions are associated with the deaths of the most massive, rapidly rotating stars. The gamma ray bursts that follow some explosions involve collapsers, massive stellar cores collapsing directly to black holes while the outer layers are still falling inward. The gamma ray bursts that follow some explosions are beamed. The energy is concentrated into narrow jets rather than emitted uniformly. If the jet points toward Earth, we see a brilliant burst. If not, we might see a normal supernova or nothing at all. The gamma ray bursts that follow some explosions are cosmic lighthouses visible across the universe. They've been detected from galaxies billions of light years away. The gamma ray bursts that follow some explosions are rare but spectacular, connecting supernova to the highest energy phenomena in the cosmos. The jets that tear through space. When a massive star collapses and forms a black hole, it can launch jets. The jets that tear through space are relativistic, material moving at significant fractions of light speed. The jets that tear through space are powered by the black hole's accretion disk, wherein falling material swirls around the black hole, heating up and releasing enormous energy. Some of this energy is channeled into narrow jets along the rotation axis. The jets that tear through space plow through the collapsing star's outer layers, eventually breaking through and escaping into space. When they do, they produce a gamma ray burst. The jets that tear through space are collimated, focused into narrow beams by magnetic fields and the geometry of the accretion disk. The jets that tear through space can extend for thousands of light years, creating structures visible in radio and X-ray observations. The jets that tear through space are among nature's most powerful particle accelerators, creating cosmic rays and high-energy photons. The jets that tear through space connect stellar death to some of the universe's most extreme physics. The collapsar model of long GRBs, long-duration gamma-ray bursts, last more than 2 seconds. The collapsar model of long GRBs explains them as the deaths of massive stars. When a very massive, rapidly rotating star collapses, its core forms a black hole. The outer layers fall inward, forming an accretion disk around the black hole. The collapsar model of long GRBs predicts that jets are launched from the black hole disk system, powered by the immense energy of infalling material. These jets bore through the collapsing star and escape, producing the gamma ray burst. The collapsar model of long GRBs is supported by observations. Most long GRBs are associated with supernovae. Observations show supernova light following the initial gamma ray burst. The collapsar model of long GRBs explains the connection between core collapse and gamma ray bursts. The collapsar model of long GRBs is still being refined. Not all massive stars produce jets, and we're still learning what conditions are necessary, likely rapid rotation and strong magnetic fields. The collapsar model of long GRBs represents our best understanding of how stellar death produces the universe's most energetic explosions. The power of magnetic fields in the blast. Magnetic fields play a crucial role in supernovae and gamma ray bursts. The power of magnetic fields in the blast helps shape the explosion, channels jets, and accelerates particles to extreme energies. The power of magnetic fields in the blast comes from the collapsing core. As the core contracts, magnetic field lines are compressed and amplified. In rapidly rotating stars, this can create incredibly strong fields. The power of magnetic fields in the blast is what launches jets and collapsars. Magnetic pressure can exceed thermal pressure, driving material outward along the field lines. The power of magnetic fields in the blast also creates magnetars, neutron stars with the strongest magnetic fields in the universe. The power of magnetic fields in the blast influences the supernova's symmetry. Many supernovae are asymmetric, with material ejected preferentially in some directions. Magnetic fields can cause this asymmetry. The power of magnetic fields in the blast is an area of active research, with simulations showing that magnetic fields significantly affect explosion dynamics. The birth of magnetars in the aftermath. Some neutron stars have extreme magnetic fields. The birth of magnetars in the aftermath of certain supernovae creates objects with fields trillions of times stronger than Earth's. Magnetars are a subclass of neutron stars, distinguished by their incredibly powerful magnetic fields. The birth of magnetars in the aftermath occurs when the collapsing core has strong rotation and magnetic fields. The collapse amplifies both, creating a neutron star wrapped in an extraordinarily powerful magnetic field. The birth of magnetars in the aftermath produces objects that occasionally release enormous bursts of energy. Soft gamma repeaters and anomalous X-ray pulsars are both thought to be magnetars. The birth of magnetars in the aftermath is still not fully understood. We know they exist. Their observational signatures are clear, but the precise mechanism that creates such extreme magnetic fields remains an active area of research. The birth of magnetars in the aftermath represents nature's ability to create the most extreme physical conditions imaginable, fields so strong they can distort atomic structure. The rotating neutron stars born from fire. Most supernovae leave behind neutron stars. The rotating neutron stars born from fire inherit angular momentum from the collapsing core, as the core shrinks from thousands of kilometers to just tens. Conservation of angular momentum causes it to spin faster, like a figure skater pulling in their arms. The rotating neutron stars born from fire can spin hundreds of times per second. The rotating neutron stars born from fire are incredibly dense, more massive than the Sun, but only about 20 kilometers across. The rotating neutron stars born from fire often become pulsars, emitting beams of radiation from their magnetic poles. As they rotate, these beams sweep across space, and if they point toward Earth, we detect regular pulses. The rotating neutron stars born from fire gradually slow down over millions of years as they lose energy through radiation. The rotating neutron stars born from fire are remnants, but they're also objects of extreme physics, laboratories for studying matter under conditions we can never recreate on Earth. The black holes that form in the dark. If the collapsing core is massive enough, even neutron degeneracy pressure can't stop it. The black holes that form in the dark are created when cores exceed about 3 solar masses. At this point, nothing can prevent further collapse. The core continues shrinking, passing through the neutron star phase without stopping, collapsing until it forms a black hole. The black holes that form in the dark are invisible. By definition, nothing escapes from within the event horizon. The black holes that form in the dark are detected indirectly through their gravitational effects on surrounding material. The black holes that form in the dark from supernovae are stellar mass black holes, typically 5 to 20 solar masses. The black holes that form in the dark represent the ultimate victory of gravity over all other forces. They're the most extreme objects that can result from stellar collapse. The black holes that form in the dark are common. Astronomers estimate millions exist in the Milky Way, most invisible, detectable only when they interact with other objects. The event horizon that swallows the core. When a black hole forms, it has a boundary. The event horizon that swallows the core is the point of no return. Once matter crosses this boundary, it can never escape. The event horizon that swallows the core grows as more material falls in. During a supernova, if the core is massive enough, the event horizon forms and immediately begins consuming the collapsing core. The event horizon that swallows the core isn't a physical surface, it's a mathematical boundary in space-time where escape velocity equals the speed of light. The event horizon that swallows the core marks the transition from neutron star to black hole. If more mass is added to a neutron star, pushing it over the limit, the event horizon forms around it, and the neutron star disappears from view. The event horizon that swallows the core represents a fundamental limit in physics. Beyond it, our understanding breaks down. We can't see what happens inside. The event horizon that swallows the core is the universe's ultimate mystery, a boundary between the known and the unknowable, the supernovae that leave no light behind. Not all core collapses produce visible supernovae. The supernovae that leave no light behind are failed supernovae or fallback supernovae, where the explosion stalls and material falls back onto the core. The supernovae that leave no light behind occur when the shock wave from core collapse doesn't have enough energy to expel the star's outer layers. Instead, those layers fall back, and the entire star collapses into the black hole. The supernovae that leave no light behind are difficult to detect. The star simply disappears. Astronomers search for them by monitoring massive stars and noting when they vanish without an explosion. The supernovae that leave no light behind might be common. Theoretical models suggest that many massive stars, particularly those in a certain mass range, might collapse directly to black holes without producing bright supernovae. The supernovae that leave no light behind challenge our understanding because we can't observe them directly. We infer their existence from theory and from the missing stars that should have exploded but didn't. The failed explosions hidden from view. Sometimes, stellar death is quiet. The failed explosions hidden from view occur when core collapse happens, but the explosion fails to propagate. The energy meant to blow the star apart is lost to neutrinos or falls back into the forming black hole. The failed explosions hidden from view leave behind black holes without producing bright optical displays. The failed explosions hidden from view are predicted by simulations. For certain stellar masses and compositions, the shock wave stalls before reaching the surface. The failed explosions hidden from view might produce brief, faint transients. Small amounts of material might be ejected before the rest falls back. The failed explosions hidden from view represent gaps in our understanding. We don't know exactly which stars will produce successful supernovae and which will fail. The failed explosions hidden from view are being searched for through surveys that monitor large numbers of stars, looking for disappearances. When a massive star vanishes without exploding, it suggests a failed explosion, a quiet collapse into darkness. The simulations that model stellar death. Understanding supernovae requires computer simulations. The simulations that model stellar death are incredibly complex, solving equations of hydrodynamics, nuclear physics, neutrino transport, and general relativity. The simulations that model stellar death take months to run on supercomputers. They follow the collapse of the core, the formation of the shock wave, the explosion, and sometimes the formation of neutron stars or black holes. The simulations that model stellar death have revealed surprising results. For years, models struggled to produce successful explosions. The shock would stall, and the explosion would fail. Only recently have simulations achieved robust explosions by including better neutrino physics and multi-dimensional effects. The simulations that model stellar death show that supernovae are asymmetric, with material ejected in clumps and jets, rather than smooth shells. The simulations that model stellar death are continuously being refined as computing power increases and physics understanding improves. They're essential for interpreting observations and predicting what we'll see when the next nearby supernova occurs. The equations that push physics to its limits, supernovae, test our understanding of physics. The equations that push physics to its limits include the equations of state for ultra-dense matter, the physics of neutrino interactions, the behavior of matter in extreme magnetic fields, and the dynamics of relativistic fluids. The equations that push physics to its limits often require approximations because exact solutions are impossible. The equations that push physics to its limits involve temperatures of billions of degrees, densities billions of times that of water, and pressures that would crush atomic nuclei. The equations that push physics to its limits connect multiple areas of physics: nuclear physics, particle physics, general relativity, fluid dynamics, plasma physics. The equations that push physics to its limits are solved numerically on supercomputers. Even then, simulations are approximations, limited by computational resources and incomplete physics. The equations that push physics to its limits show that supernovae operate in regimes where our understanding is incomplete. They're natural experiments, testing physics in conditions we can never reproduce in laboratories. The neutrinos that escape first. When a star's core collapses, most of the energy escapes as neutrinos. The neutrinos that escape first carry away about 99% of the gravitational energy released by the collapse. These neutrinos barely interact with matter, streaming out of the collapsing core at nearly the speed of light. The neutrinos that escape first reach detectors on Earth hours before the light from the explosion, because they don't have to wait for the shock wave to reach the star's surface. The neutrinos that escape first were detected from supernova 1987A, confirming this prediction. The neutrinos that escape first are difficult to detect. They interact so weakly that even enormous detectors capture only a handful, but those few detections are invaluable, providing direct evidence of core collapse and confirming that neutrinos carry the collapse's energy. The neutrinos that escape first represent one of the universe's great inefficiencies. Enormous energy is released but carried away by particles that barely interact with anything. Yet this inefficiency is what makes supernovae possible. The particles that tell the story before light. Neutrinos are messengers from the core. The particles that tell the story before light arrive at Earth hours before the optical explosion becomes visible. This is because neutrinos escape immediately when the core collapses, while light has to wait for the shock wave to tear through the star's outer layers. The particles that tell the story before light provide early warning. When neutrino detectors see a burst, astronomers know a supernova is happening somewhere, even before it's optically visible. The particles that tell the story before light can help pinpoint the supernova's location. Multiple detectors at different locations see the burst at slightly different times, allowing triangulation. The particles that tell the story before light are being monitored continuously. Networks of neutrino detectors around the world are connected, ready to alert astronomers when the next galactic supernova occurs. The particles that tell the story before light provide unique information about the core collapse, information that can't be obtained any other way. The observation of a star's final moments. For the first time with supernova 1987, astronomers observed a star before and after its explosion. The observation of a star's final moments revealed the progenitor, a blue supergiant star, catalogued as Sanjo Lake, minus 69 degrees, 202. The observation of a star's final moments showed that the star had been evolving, changing in the years before explosion. The observation of a star's final moments continues today with surveys that monitor thousands of massive stars waiting for the next explosion. The observation of a star's final moments includes photometry and spectroscopy, measuring brightness and spectrum, looking for changes that might signal imminent collapse. The observation of a star's final moments could provide crucial insights. Do stars brighten before exploding? Do they show spectral changes? How much warning do we get? The observation of a star's final moments is a goal for supernova astronomy, to catch a supernova in the act, to see the light curve from the very beginning, ideally with neutrino detection confirming the core collapse. The observation of a star's final moments would be the ultimate validation of supernova theory, the light curves that reveal the explosion's strength. After a supernova, astronomers measure its brightness over time. The light curves that reveal the explosion's strength show how the supernova brightens, peaks, and fades. Different types of supernovae have different light curves. Type Ia supernovae rise quickly, peak after about 2 weeks, then decline steadily. Type 2P supernovae have a plateau phase where brightness stays roughly constant for months. The light curves that reveal the explosion's strength depend on the explosion's energy, the amount of radioactive material produced, and the star's structure. The light curves that reveal the explosion's strength are analyzed to determine the explosion's total energy, the mass of material ejected, and the composition of that material. The light curves that reveal the explosion's strength are particularly important for type Ia supernovae, which are used as standard candles. By measuring the light curve's shape and peak brightness, astronomers can precisely determine the supernova's distance. The light curves that reveal the explosion's strength are datasets that encode the explosion's physics, waiting to be decoded by careful analysis. The spectral lines that map its composition. Spectra reveal what supernovae are made of. The spectral lines that map its composition show absorption or emission at specific wavelengths, each corresponding to particular elements. Hydrogen produces lines in the red and blue parts of the spectrum. Silicon, oxygen, iron. Each element has a unique spectral signature. The spectral lines that map its composition allow astronomers to classify supernovae and understand what was in the star before it exploded. The spectral lines that map its composition change over time. Early spectra show the outer layers. Later spectra reveal deeper material as the expanding gas becomes transparent. The spectral lines that map its composition are Doppler shifted, revealing the explosion's velocity. Material moving toward us appears blue shifted. Material moving away appears red shifted. The spectral lines that map its composition can show that explosions are asymmetric, with different velocities in different directions. The spectral lines that map its composition are fingerprints, unique to each supernova, yet following patterns that allow classification and physical understanding. The dust that grows from cooling remnants. After a supernova, the ejected gas cools. The dust that grows from cooling remnants forms when temperatures drop enough for atoms to stick together, creating tiny solid particles. The dust that grows from cooling remnants includes silicates, carbon grains, and other refractory materials. The dust that grows from cooling remnants is important for several reasons. It affects how we observe the supernova, absorbing and scattering light. It's also important for the galaxy. This dust becomes part of the interstellar medium, providing the raw material for future planets. The dust that grows from cooling remnants has been observed in young supernova remnants, including supernova 1987. Observations showed dust forming in the cooling ejecta just years after the explosion. The dust that grows from cooling remnants is one way the universe creates dust. Along with dust from stellar winds, supernova dust enriches galaxies, making planet formation possible. The dust that grows from cooling remnants connects stellar death to planetary birth, closing another loop in cosmic recycling. The nebulae that glow for centuries. Supernova remnants are beautiful. The nebulae that glow for centuries are expanding shells of gas, heated by the supernova shock wave, glowing across the spectrum. The nebulae that glow for centuries include famous objects like the Crab Nebula, Cassiopeia A, and the Vela Remnant. The nebulae that glow for centuries are dynamic, changing over years and decades as the shock wave expands and interacts with surrounding material. The nebulae that glow for centuries eventually fade as the shock wave slows and the gas cools and disperses. Young remnants, just decades old, are bright and compact. Old remnants, thousands of years old, are faint and large, blending into the interstellar medium. The nebulae that glow for centuries are laboratories for studying shock physics, particle acceleration, and the interaction between supernova ejecta and the interstellar medium. The nebulae that glow for centuries are cosmic artwork, intricate structures shaped by physics, beautiful to observe, revealing the aftermath of stellar violence. The beautiful remains seen by Hubble. Some of the most stunning images in astronomy are of supernova remnants. The beautiful remains, seen by Hubble, include detailed views of the Crab Nebula's intricate filaments, Cassiopeia A's complex shells, and the delicate rings around supernova 1987A. The beautiful remains seen by Hubble reveal structure invisible from ground-based telescopes, knots, filaments, shells within shells. The beautiful remains seen by Hubble are colored to represent different elements or temperatures, creating images that are both scientifically informative and aesthetically striking. The beautiful remains seen by Hubble show that supernova remnants are not simple spherical shells but complex, three-dimensional structures shaped by asymmetries in the explosion, the progenitor star's structure, and interactions with surrounding gas. The beautiful remains seen by Hubble are analyzed to understand explosion dynamics, element distribution, and the remnants' evolution. The beautiful remains seen by Hubble remind us that science and art intersect, that the universe creates beauty even in destruction, that stellar death produces structures of haunting loveliness. The expanding shells of cosmic art. Supernova remnants are sculptures. The expanding shells of cosmic art are shaped by fluid dynamics, magnetic fields, and the environment. The expanding shells of cosmic art include symmetries and asymmetries, arcs and filaments, bubbles and wisps. The expanding shells of cosmic art change over time. The Crab Nebula looks different now than it did decades ago, its structure evolving as the pulsar's wind reshapes it. The expanding shells of cosmic art are three-dimensional, though we see them projected onto the sky. Astronomers use velocity measurements and geometric modeling to reconstruct their true shapes. The expanding shells of cosmic art are evidence of violent events transformed into beauty. The expanding shells of cosmic art will eventually disperse, their material mixing with the interstellar medium, becoming part of future stars. The expanding shells of cosmic art are temporary, but while they last, they're spectacular, combining physics and aesthetics in structures that inspire wonder. The Cassiopeia A remnant and its story. Cassiopeia A is one of the youngest and brightest supernova remnants in the Milky Way. The Cassiopeia A remnant and its story began about 340 years ago, though the explosion wasn't recorded, possibly because dust obscured it from Earth. The Cassiopeia A remnant and its story shows an asymmetric explosion, with jets and clumps of material moving at thousands of kilometers per second. The Cassiopeia A remnant and its story includes a neutron star at the center, detected in X-rays, rapidly cooling since its formation. The Cassiopeia A remnant and its story has been extensively studied across the spectrum. X-ray observations show the hot interior. Optical observations reveal fast-moving knots. Infrared observations detect dust forming in the cooling ejecta. The Cassiopeia A remnant and its story provides insights into explosion mechanisms and the formation of heavy elements. Observations show silicon, sulfur, iron, and other elements distributed asymmetrically through the remnant. The Cassiopeia A remnant and its story is a textbook case, studied in detail, revealing the complexity of supernova explosions. The echoes of light that circle the past. Some supernova remnants show light echoes. The echoes of light that circle the past occur when light from the original explosion travels through space, hits dust clouds, and reflects toward Earth. Because the light takes a longer path to the dust and then to Earth, it arrives years or centuries after the direct light. The echoes of light that circle the past allow astronomers to observe ancient explosions. By studying reflected light from historical supernovae, they can obtain spectra and classify explosions that occurred centuries ago. The echoes of light that circle the past have been observed around Tycho's supernova and supernova 1987. A. The echoes of light that circle the past are like time machines, bringing light from past events to the present. The echoes of light that circle the past are beautiful phenomena, rings or arcs of light, expanding outward from the remnant center, marking the supernova's original brightness. The echoes of light that circle the past are temporary, visible only while the light is reflecting off nearby dust, then fading as the expanding light sphere moves beyond. The galactic supernovae, yet to come. Our galaxy's next supernova is waiting. The galactic supernova yet to come are inevitable. With hundreds of billions of stars, some massive ones will explode. Statistically, 1 or 2 supernovae should occur per century in the Milky Way. The last observed galactic supernova was Kepler's in 1604. We're overdue. The galactic supernova yet to come will be spectacular. A nearby supernova, within a few thousand light years, would be visible in daylight, transforming the night sky. The galactic supernova, yet to come, will provide unprecedented scientific opportunities. Modern instruments will capture every detail: neutrinos, light across the spectrum, the evolution of the explosion, from first light to remnant formation. The galactic supernova, yet to come, could occur tomorrow or in 100 years. We don't know, but astronomers are prepared, with networks of telescopes and detectors ready to turn toward the explosion to capture data that will advance our understanding of stellar death. The galactic supernova yet to come are cosmic gifts waiting to be unwrapped. The role of supernovae in cosmic chemistry. The universe started with only hydrogen and helium. The role of supernovae in cosmic chemistry is creating everything else. Through stellar fusion and explosive nucleosynthesis, supernovae produce carbon, oxygen, silicon, iron, gold, uranium, all the elements heavier than helium. The role of supernovae in cosmic chemistry is scattering these elements into space, enriching the interstellar medium. The role of supernovae in cosmic chemistry is enabling complexity. Without heavy elements, there would be no rocky planets, no water, no organic molecules, no life. The role of supernovae in cosmic chemistry has been ongoing for billions of years, gradually increasing the abundance of heavy elements in the universe. Early stars formed from pure hydrogen and helium. Later generations contain more metals, built from the ashes of earlier stars. The role of supernovae in cosmic chemistry is fundamental to the universe's evolution, transforming a simple, uniform cosmos into one rich with chemical diversity. The life, death, and rebirth of stars. Stars are born, live, and die. The life, death, and rebirth of stars is a cycle. Gas clouds collapse to form stars. Stars burn for millions or billions of years. They die, either quietly or explosively. Their material is scattered into space. That material mixes with interstellar gas, enriching it. New stars form from the enriched gas. The cycle repeats. The life, death, and rebirth of stars is continuous, ongoing throughout the galaxy and universe. The life, death, and rebirth of stars means that matter is constantly recycled. The atoms in your body have been through multiple stars. They've been fused, scattered, reformed, scattered again. The life, death, and rebirth of stars is why the universe is chemically evolving, why each generation of stars is slightly different from the last. The life, death, and rebirth of stars will continue for trillions of years until the universe runs out of gas to form new stars. But that's far in the future. For now, the cycle continues, stars dying and being reborn in an endless cosmic rhythm. The story of energy returning to the universe. Stars lock up energy and matter through fusion. The story of energy returning to the universe is supernovae releasing that energy. Fusion creates heavy elements, binding energy in atomic nuclei. When a star explodes, some of that energy is released, but more comes from gravitational collapse. The story of energy returning to the universe is gravity's potential energy converted to kinetic energy, heat, and light. The story of energy returning to the universe is the shockwave carrying energy into the interstellar medium, heating gas, driving galactic winds. The story of energy returning to the universe is cosmic rays accelerated by supernova shocks, carrying energy throughout the galaxy. The story of energy returning to the universe is neutrinos streaming outward, carrying energy beyond the galaxy entirely. The story of energy returning to the universe is continuous. Every supernova adds energy to the galactic environment, shaping its evolution, maintaining its dynamism. The story of energy returning to the universe is one of transformation, bound energy becoming free, potential becoming kinetic, stillness becoming motion. The endless cycle of destruction and creation. Destruction and creation are one. The endless cycle of destruction and creation is the universe's fundamental pattern. Stars destroy themselves in supernovae, but those explosions create heavy elements, trigger new star formation, shape galaxies. The endless cycle of destruction and creation means nothing is ever truly destroyed, only transformed. The endless cycle of destruction and creation operates on all scales, from atoms to galaxies. The endless cycle of destruction and creation is why the universe is interesting, why it's complex, why it evolves. Without destruction, everything would be static, unchanging. Without creation, the universe would wind down, becoming cold and dark. But with both, the universe remains dynamic, alive, full of possibilities. The endless cycle of destruction and creation is beautiful in its balance, terrible in its violence, profound in its implications. The endless cycle of destruction and creation is the engine of cosmic evolution, the process that turned the simple post-Big Bang universe into the rich, complex cosmos we inhabit today. The light that never truly dies. When a star explodes, its light travels forever. The light that never truly dies continues spreading outward at light speed, carrying information about the explosion to distant corners of the universe. The light that never truly dies means that every supernova ever seen from Earth is still radiating outward, visible now to civilizations billions of light years in other directions. The light that never truly dies is one way the universe preserves its history. Light from ancient events still traveling, still carrying information. The light that never truly dies connects all observers. Someday, trillions of years from now, civilizations we can't imagine will see light from supernovae that occurred in our time. The light that never truly dies is metaphor and reality. Stellar death produces light that endures, spreads, never vanishes, always traveling, always carrying the story of that star's final moment. The light that never truly dies is the universe's memory, information preserved in photons, spreading outward forever, ensuring that no stellar death is truly final, that every explosion leaves a permanent mark on the cosmos, visible to whoever might be watching, wherever and whenever they might be.